Yes, you look good. Go ahead.
Okay. Hi everyone. My name is Xiaolin Wen from Nanyang Technological University, Singapore, and I'm glad to be here to share our work, DiffSeer, Difference-Based Dynamic Weighted Graph Visualization. This work was done in collaboration with Sichuan University and Singapore Management University. So first, let's start from what is dynamic weighted graph. Dynamic weighted graph is a weighted graph like this, and it can change over time. Like the edge weights will be different in different time slices. And this dynamic weighted graph can model the temporal evolution of relationships between entities in various applications, such as the social network, financial network, or communication network where the nodes are these entities and the changing edge weights indicate the dynamic relationships. It is crucial to visualize such dynamic weighted graph to help user review the temporal evolution process. And previous visualizations about it mainly falls in two categories. The first one is time-to-time mapping. It means use animations to show the dynamic changing process about the graph. And another one is the map the time to space. It's like the small multiples. They show all the time slices along a timeline and ask user to see all the time slices simultaneously. However, both two methods have some problem. To identify the changes, user need to mentally compare the differences between multiple adjacent time slices simultaneously. It is a challenging task because the differences in dynamic weighted graph is too complex and subtle to identify. It will be more challenging when we have so many time slices like this. And when we show the differences explicitly, like we show the differences between two time slices and highlight the increasing and decreasing edge weight with red and blue, it will be easy to identify the changes between two time slices. And when we show a sequence of differences between adjacent time slices, we can quickly identify the changes of dynamic weighted graph over a period without mentally comparing the graphs. And additionally, we can find some interesting pattern here. If we only see these two black dynamic weighted graphs, we cannot find some relations between them. But if we see their different sequence, we can find it's the same. It indicates that the same changing pattern occurred in different contexts or in different period. If we don't show the differences explicitly, we cannot find this pattern. So inspired by this idea, we propose difference-based dynamic weighted graph visualization. It's called DiffSeer, and it's used to support more time slices and help to track significant changing patterns like the recurring changes. Next, I want to mainly focus on two main parts. The first one is the nested matrix design, and another one is the difference mask to help track the changing pattern. Then I will introduce them one by one. First, the nested matrix design aggregate the different sequence into a matrix called overview matrix. Each row of overview matrix represents a node, and each column is one time slice. Each cell here summarizes the changes on one node in one time slice. In this matrix, we can easily overview the overall changing patterns of a dynamic weighted graph. And after that, if you want to check the detailed changes of each time slice, you can double click on a column to unfold a difference detail matrix to see the difference map here. And you can also click to check the original graph detail matrix. This is what we call the nested matrix design. And if you want to understand the period changing pattern, you can check the original graph at the start and the end of this period and see the differences occurring in the middle. And it can help you quickly to analyze a long period. And however, the node order in this matrix is very important. If the matrix do not have a good node order, it is hard to find some insights from it, like the clusters and communities. As I mentioned, we have three different types of matrix here. So how to make all those matrices have good visual patterns is very important. So therefore, we propose an adjustable global node reordering strategies. This strategy can help user to make the node order is suitable for both overview and the detail matrices. And furthermore, we also provide some auxiliary charts to offer statistics. Like we use a stacked bar chart to show how many nodes changed in each time slice, or we use a error chart to show the frequency of edge changes on each node. And next, I will introduce the difference mask. Difference mask is designed for tracking the significant changes in overview matrix. It first select and highlight the nodes with significant changes. And after that, we connect the highlighted nodes in one time slice and to show the similar patterns in one time slice. After that, we connect the highlighted nodes across time slices. It can help to track the recurring pattern or the transition of changing center or some stable period without any links. Next, I will use a demo to showcase how to use DiffSeer to analyze a financial network. This network is a sector index correlation network of China stock market. And the nodes here are 28 sector indices, and the edges are the correlation between any two indices per day. And if the edge weight increased, it means two indices have the similar changing pattern. And if the edge weight decreased, it means these two indices have a different changing pattern. Okay, let's see the video.
Here is the prototype system of DiffSeer. Firstly, we can get a rough overview of the original dynamic graphs in a timeline view. Then, after brushing a period of interest, such as the period after the COVID-19 outbreak, the nested matrix design shows the temporal evolution patterns during this period below. In the overview matrix, we can easily overview where the changes occur and check their characteristic. It also can be seen that some nodes with significant changes are highlighted and connected by the difference mask to emphasize their similar change patterns. After the COVID-19 outbreak, we can notice two periods with a significant increase of the sector correlations and several sectors with obvious negative changes, and the network has barely changed after March. Unfolding the original graph context by double-clicking a column and reordering the nodes, we can see that after the first significant correlation increase, the network spread from local association to global association. Or you can unfold any difference detail matrix you want to get more insights. According to a financial expert, the interesting patterns above have resulted from two stock market crashes and a series of work and production resumption policies under the COVID-19.
Okay.
Here is the
For evaluation, we conduct two case studies on two real-world data set to tell if DiffSeer can work well on different scenario. And we also conduct an expert interview with 12 graph analysts to get their feedbacks. And the results looks DiffSeer is useful. Okay, in conclusion, in this paper, we propose a novel visual design called DiffSeer. It's designed for dynamic weighted graph visualization. And we explicitly visualizing the differences between adjacent time slices. And in this visual design, we propose a nested matrix design support the flexible exploration across numerous time slices. And we also provide a difference mask to support tracking significant changing patterns. Okay, that's all my presentation, and thanks for all the audience and co-authors. For more detail, please check our paper. Welcome any questions about this work.
Thank you, Xiaolin. Appreciate that contribution to our community. Very attractive looking paper. Everything made sense in your communications. If anybody has any questions, including our other presenters, please put them into Slido. We have one question so far, which I'll ask, which says, did you consider the similarity of weighted graphs at different time moments? Pairwise similarities of times could create one more matrix for your framework.
Now we only consider the similar pattern in adjacent time slice. If they appeared in different time period, we don't have any highlighting or something to show it on our visualization.
Do you perceive that as having some value as a future feature of your work?
No. There's no some value to as a matrix to tell the similarity, but we just to detect the and for now we just use the edge weight, the max edge weight. If it's exceeds some threshold, we will regard it as a strong changed node, and we will highlight it and link those strong changed nodes across the time slices. And the threshold can
Yes.
set by the user.
Yes, very nice. Thanks again. I wanted to say that the two user expert case studies were really useful for me because it kind of confirmed my expectations in terms of human behavior to those situations. So it was really nice to see that your tool reinforced my understanding. And of course, you want to also use such tools to have insights that you weren't anticipating as well, which would definitely arise with the right data. So thank you very much. We're going to go on to our next presenter. Our next presenter is Maureen Stone. I'll let her introduce her co-authors and her paper. Thank you, Maureen.
All righty, let me get this all set up and not interfering with each other here.
That looks good.
Excellent. All right. I'm here to defend the rainbow color map. The goal of my talk is to persuade you that rainbow color maps are not all bad. Now, I want to point out that this is a visualization viewpoint. It is not a research paper, but an opinion piece. So who are we to take on the standard wisdom that rainbows are bad? Well, as you can see, among us, we have many years of work in color, perception, visualization. Colin has been at it since the 80s and has written the definitive text on the topic. I also have been working in color since the 80s, but I didn't get into the visualization area until I started doing color maps for Tableau. Danielle is a relative newcomer, but she and her students have put together a remarkably excellent body of work. If you don't know her already, you should go find out. So, what motivated this work? Well, Colin came to Danielle and I, and he said, you know, for many, many years, maybe 20 years, maybe 25 years, we as a community have been complaining that the rainbow color map is bad visualization practice. And yet, practitioners continue to use it. They seem to like it, they're getting real work done, and they prefer it over more correctly designed color maps. So maybe it's time to ask why. Instead of continuing to preach about why rainbows are bad, we should say, how can rainbows be good? And I want to pause here and point out the work of Carrie Retta, who is also asking this question. So why are rainbows a problem? Well, they have irregular luminance profiles which obscure shape from shading. They're not perceptually uniform. The hue partitions the data, sometimes arbitrarily, and they're difficult to make accessible. And so the structure of this talk is to go through each of these points in turn. But before I do that, let's ask and answer, what is a rainbow color map? Well, we decided that it is any color map that maps data through the rainbow hues in order: blue, green, yellow, orange, and red. And here are 6 of them. The ones on the left are created by a simple RGB interpolation, like around the HSV hue circle. They're all essentially the same. The first one trims off, is the whole hue circle. The second trims off the magenta, and then jet darkens the ends a little bit for better contrast. The ones on the right are perceptually crafted. That is, they have been designed knowing the problems that I just put on the previous slide. ParaView Uniform was designed by Colin. Turbo was designed at Google. It's similar to ParaView Uniform, but somewhat more rounded and smoothed in the center. And then this qubit thermal imaging one is idiosyncratic, but is used in the thermal imaging product. Point number 1, when you talk about a rainbow, which one are you talking about? So back to our problems. Irregular luminance profiles. Well, what do we mean by that? So what's luminance? Luminance is simply perceived lightness. And here's an image that I use in almost all my color talks. If you take a scene or a picture, you can split it into the lightness information and the color information. And all the interesting information is in the lightness channel. And that is, you can see the shape, you can see the contrast, you can see all the details. The color is just sort of a gloss over the top, and this is fundamental to vision. It's also why grayscale photography works. Now, a lightness profile simply maps data values to some perceived lightness metric, like luminance, or I prefer L star because it's more perceptually uniform. The profiles on the left are monotonic. They go from min to max with no doubling back. To preserve shape from shading, you need a monotonic lightness profile. It doesn't need to be linear like the blue one, although linear and L star is an excellent profile for a visualization color map. It just needs to be monotonic. The gold one would work as well. However, not all visualization applications require shape from shading. And in many cases, we've found a bilinear profile to be extremely useful, say for diverging color maps. So that means you have a color on one side that goes from dark to light, and then a different color on the other side that goes from light to dark. So what about our rainbows? Well, if you look at the old-fashioned classics, they all have about the same profile, and it's kind of a mess. It's not very predictable. On the right, however, they've been crafted to be bilinear. The Paraview uniform is strictly bilinear, Turbo is more rounded, and the qubit imaging one is multi-bilinear. So it's actually pretty easy to make a rainbow have a bilinear-ish color profile because both ends are dark, red and blue, and the colors in the center are naturally light. It's impossible to make it monotonic if you use the bright colors, but you can do it if you're willing to make one end more pastel. Perceptual uniformity. A data step equals a perceived color difference. So ideally, you could use a delta E value in CIE lab to create uniform perceptual steps along your color map. But in practice, uniform delta L star gets you most of the way. And this is from research of Colin, and it actually makes sense if you understand the importance of luminance for understanding shape and detail. Now, hue banding. Hue banding, I think, is actually pretty good. Hue change creates categories. We know categories are great for cognition of color, that they group, they're memorable. That's why they work for categorical color maps. It also facilitates reading values from a key, and it can highlight a global data structure and data distributions. The problem with the rainbows, especially the classic ones, is that the hue banding tends to be arbitrary, and that's bad. But you can fix that if you control the data to hue mapping and make it have semantic meaning. Now those bins are very powerful. So for example, in the weather map, we have some clear colored bins, and they sort of line up with decades. Anything that's reddish orangish is above 80. There's this sort of yellow region between 60 and 80. There's a slice at green in between 50 and 60. It's memorable. It's easy to see on the map everything that is the same hue, that is in the same data range. The thermal imaging is the same, only it has more detail. That's what that zigzaggy map gets you. I don't know if how well those colors actually align with interesting semantic values, but for a practitioner, if they're using more or less the same scale, the colors and the color images give you a really good overall perception of how the sample is reacting. Let's look at this MATLAB function plot. Here it's a Z is positive and negative. It's a bunch of sines and cosines. And the author has put the center of the turbo color map there at 0. So 0 is this yellow-green color, and you can immediately see in the plot how clearly where 0 is in this plot. Anything above 0 is red and orange. Anything below or 0 is blue. It's an interesting way to analyze that z-axis. In contrast, the more correctly designed multi-hue map on the right does that a little bit, but nowhere near the same level of detail. So, for my final problem, they're difficult to make accessible. So let's look at this simulation. On the left, we have the full color version for normal trichromats. On the right, we have the 2-cone version dichromats, the most extreme form of color blindness. And in between, we have the anomalous trichromat. Now, if you have CVD, your perception of luminance is very similar to those of us with more normal color vision. However, hues start to collide. And in the dichromat case, you can see the rainbows. It's pretty hard. You have all of these colors in the center that are more or less the same, green, orange, and yellow. But if you don't have full-on CVD, because the colors are bright, it's often possible to still make sense of the rainbows, especially the perceptually crafted ones. So in conclusion, I hope I have persuaded you that we understand well enough what makes rainbows bad. And now it's time to move forward and understand where they can be good. And to do that, we need to think about which rainbow and which task. A rainbow, after all, is just an extended multi-hue. Multi-hues do well at various tasks, so should the rainbow. So please, when you think about evaluating rainbows or designing with rainbows, think carefully about which rainbow, and don't use the old classics if you already can tell they're going to fail. Data to hue mapping is important. There seems to be a pattern where people take raw data and they throw a color map on it and they start looking for insights. But you can do better than that. You can, for example, normalize your data so that now what you have is quantiles, and then you can line the quantiles up with hue boundaries. And now you have a really useful a color ruler, shall I say. And finally, about accessibility, I think we have a lot more to learn. And I don't mean this just for rainbow color maps, but for viz in general. It's a complicated area. A lot of what I see in terms of recommendations for accessibility for CVD are fairly simplistic. I think we need to do better. And that ends my story. And back to you, Bruce.
All right. Thank you very much, Maureen. Appreciate that. Applause from everybody. I know that that's a contribution that my students will appreciate. The color map discussion of the data visualization course we have at RISD is always one of the most popular places for people to have their opinions, and this adds to a richness in that. I'm looking for any questions from the audience, and I don't see any on Slido. I have about 40 that I can imagine my students asking, but in the timing of the session, I see that we're just about a minute past where the next presenter should present. So if you don't mind, we'll just go into that, and we can continue any questions or discussion on Discord, and all the authors' email addresses are available from the session page. Thank you again, Maureen. Very nice.
Thank you.
Next presenter is Yuxin Liu. He's going to introduce his co-author and his paper, and take it away, Yuxin.
Thank you, Bruce. Can you hear me?
Yes, your sound is strong and clear. Thank you.
Okay, thank you very much. Thank you for the introduction. My name is Yuxin Liu. Now I'm doing research fellow at the University of Leeds. This paper is one of my work during my PhD. I co-authored with my previous supervisor, Homa Voimo, working at the Gotz at Lyon. Today, the topic that I introduce is about generic interactive membership function that can help a human to categorize the quantities. Okay, now Let's start from the motivation. Let's look at some characters from the Simpson cartoon. Generally, they have the different ages. So how do we categorize the characters based on their age? Normally, we give them the different labels like adult, senior, children, and so on. Let's go back to the data set here. They have the different names and look at the data age. There are some quantities. And after the categorization, we have the results like age group. They have the different labels, children, adults, and so on. They are categories. So from the quantities to categories, there are some mapping function. The mapping function could express the relation between elements in the quantities and the elements in the categories. So in this process, progress, we have there is a need that is an interactive mapping function to capture some information such as the name of categories, the intervals, the labels of categories, and so on. About this work, there are some relevant work about such as the fuzzy visualization and the mapping function. Speaking of the fuzzy visualization, there are some typical or related works like a fuzzy disk diagram, fuzzy bubble, fuzzy rows diagram, fuzzy networks. Generally, all of these visualization techniques usually use the different shapes to express how confident that a number belonging to a specific category. In the part for the mapping function, here is the traditional mapping function. In this work, we tried to expand the membership this mapping function. Let's go to the details of the traditional mapping function. It's a typical line chart here. In this line chart, the x-axis refers to the quantities, and the y-axis refers to the membership values. As we can see, this mapping function has the clear boundary, and the membership values are either 0 or 1. We're using this mapping function to categorize the ages for characters like this. We can categorize it as children, this one as the senior. But what if some character, they are very close to the boundary here? Normally, in our brain, we don't have a very clear boundary in our brain while categorizing the quantities. So there are some uncertainty. So our idea is to use the fuzzy membership function to give the confidence for each character ages. For example, let's take this example. We'll categorize the age of this character. We give them the two membership values to express how confident that it belongs to the different categories. It has 90% confidence that belonging to adult and only 10% confidence belonging to the senior. It is our idea, and we developed it an interactive membership function. Is the overview. It contains three views, parameters, membership function, and the data table. In this interactive membership function could address three tasks. Task 1 is to adjust the mapping function. Task 2 to express the mapping process. Task 3 to name the derived categories. So our three views could address the three tasks. For example, the parameters could adjust the shape for mapping function. The membership function could explicit the mapping process. The data table could name the derived categories. Let me introduce how to use it using a video. Here, we can adjust the parameters so that the shape of the membership function could also be changed. After changing the shape of the membership function, we can get the different categories with the different membership values. And also, we can also check the name of generated categories, and also we can change the name of them. As we can see, after change it, the fuzzy categories could be changed. All the items in the data could be changed. Now let's move on to the user study. In the user study, we proposed three hypotheses. Hypothesis 1, our tool could affect the categorization results. Hypothesis 2, the number of data items would affect the categorization results also. Hypothesis 3, users would express the uncertainty categories with comparative and descriptive words. By doing this, we first recruited several participants in our lab and other lab. They are both PhD students or the masters. After that, we invited them to fill in a questionnaire to collect some basic information, for example, the age, the gender, and so on. And then we invited them to use our tool to categorize the two data sets. They are general data sets such as data and the temperature. Eventually, we also invited them to fill in another questionnaire to collect the feedback after using our tool. Here is one of the results. To verify the hypothesis 2, we raised a question. Are the categorization results same while categorizing the whole dataset and the sub-datasets? We want to know if the number of data items could affect the results that their categorization. Let's look at these two boxes. They are showing the different number of data sets and the results. The results are the numbers of total categories. They are different, so it verifies the results. The hypothesis 2, the counts of categories being different shows categorization is affected by the number of data items. For the hypothesis 3, how do people name the generated categories? We collected all the words the participants used while using our tool and visualized them with the word clause. As we can see, the words they prefer, like the very, small, middle, some words like this. So we can conclude that people tend to name the generated categories with the comparative and descriptive words. Eventually, do they like our tool? Is corresponding to the hypothesis 1. How do people feel our tool? They collected the results from the questionnaire and visualized it using Likert scale. the resources is easy to interact and help people categorize the quantities. Furthermore, we also applied our tool by connecting it with other visualization techniques. For example, in this example, the number one is our tool. The number two is another visualization. We can use our tool as an interactive legend to create different categories by interact with our tool, so that by doing this, we can interactively observe the changes in another visualization. To summarize, we developed an interactive membership function, conducted user study, and did some further application. That's my introduction. That's my paper. Thank you. Thank you very much. I'm happy to take any questions.
Hi, Shen. Thank you very much for that presentation. I think it'd be very interesting to use your tool in conjunction with people's descriptions of color maps to see how they would categorize different colors from a map and try and figure out how many different categories a color map provided naturally from how they experienced it. So I see many places of application. I'm looking at the Slido. We don't have any questions. I don't know if anybody's holding one. Anybody want to speak up within our group for a question? You're welcome to do so, but we really should move on given the times that are identified for our papers. So thanks again.
Thank you. Thank you, both. Thank you.
Thank you. Okay, so the next presenter is Laura Matzen. She has a team of four authors that she can introduce, and I'll let her introduce her paper. Thank you, Laura.
Great, thank you. So I'm Laura Matzen from San Diego National Labs, and I'm presenting this work on behalf of my co-authors, Howell, Mike Trumbo, and Kristin Divis. All right, so we know from prior work that presenting information in different ways might change how people perceive and reason about risk. And in particular, there are a few prior studies that have looked at visual representations of probability and have found that those can sometimes lead to more risk-averse decisions than numerical or verbal representations of the same information. And this difference tends to decrease if the information is more specific. So if people are given, say, a small range of probabilities to reason about, it probably doesn't matter if it's presented visually or numerically. But if people are given a wider range of probabilities that's less specific, that's when these prior studies have shown a tendency for people to make more risk-averse decisions with visual representations of probability. So there are a couple reasons this might be happening. The first is that the visualizations might make the risk seem more concrete or more deterministic to the viewer. So maybe when people see a visualization of a risk, it makes them consider that risk more carefully or think about it more, and that could lead to more risk-averse decision-making. Another possibility is that when people are shown a range of probabilities, they might be trying to estimate a point value to base their decision on, and that process may be harder when it's a visual representation. And so in my lab at Sandia, we've been doing a line of research related to how to represent risks from wildfires. And so for our work, it was important to dig in and figure out the reasons behind this effect, because we want to know, if visualizations tend to make people lean towards more risk-averse decisions, we want to know if we don't want to unintentionally bias people. And so we've decided to do some work to dig into this question and figure out, which of these factors was leading people to make more risk-averse decisions with visualizations. And the short answer is it's both, but I'll describe our studies and explain how we got to that answer. So in this paper, we presented two experiments. Both of them represented point probabilities as icon arrays or natural frequencies. And the important distinction between this and the prior work is that we were using point probabilities instead of a range of probabilities. So we, in theory, eliminate the need for people to estimate the probability before making their decision, because we wanted to focus in on how the visual features themselves were impacting people's perception of the risk. In experiment one, we manipulated the perceived specificity of the information. So we gave people the same percentages in every case, but we changed the denominator of the icon array or the natural frequency. We changed the iconicity and the order in the icon arrays. In experiment 2, we increased the actual specificity of the information. So for example, instead of presenting a probability of 6 in 10, we changed it to 61 out of 100. So we made the information more specific. As I mentioned, this is part of a line of research about how people judge wildfire risks. And so we gave them a wildfire-related task. So this was done on Amazon Mechanical Turk. And on each trial, people were shown a stimulus showing the probability of their house being in the burn zone of wildfire. They made a decision to stay or to evacuate. And then they saw the outcome of that scenario. Was their house safe or was it in the burn zone? And their decisions were tied to monetary payments. So people on Mechanical Turk are very motivated by this kind of thing, and we wanted to motivate them to make the best decisions possible given the probabilistic information they were given. So each time they made a correct decision, they earned 5 cents. Each time they chose to evacuate, that cost 2 cents, and that represented the fact that evacuating in real life has costs. But if they chose to stay in the house and it ended up being in the burn zone of the fire, they lost 10 cents from their bonus. So again, this isn't a real replication of making this decision in real life, but we wanted to motivate people to do their best with the probabilities they were given and to reflect the fact that these different choices have different costs. So we used 10 different versions of the stimuli. So we showed the same percentages of the risk as natural frequencies, as shown in the top row there, or as icon arrays. And as I mentioned before, we manipulated the perceived specificity of the information. So the icon arrays could have 10 icons or 100. They could have the low iconicity square icons, or they could have the higher iconicity house icons. And they could be ordered or randomized. And prior research on icon arrays has shown that these are all factors that might change people's perception. The randomization might lead people to be more aware of the probabilistic nature of the outcome. So that's why we included that condition. So in terms of our results, our main question was, would we see differences between the icon arrays and the natural frequencies? And we did. So overall, people were significantly more likely to evacuate when they saw the icon arrays than the natural frequencies. At the extremes, when the probability of the house being in the burn zone was very low or very high, it didn't make much difference. But in the middle of the scale, we saw this tendency towards more risk-averse decisions with the icon arrays. When we look at the details of the different types of icon arrays, we found that participants were more likely to evacuate when the icon order was randomized. And unsurprisingly, this effect was driven by the 100 icon arrays. So for the 10 icon arrays shown here, there wasn't really any difference between ordered and random, but we do see this difference for the 100 icon arrays, where people were more likely to evacuate when they were randomized. And I'll talk a bit more about that with experiment 2. We also found a significant interaction between the iconicity and the ordering of the icons. So for the ordered icon arrays shown in this purplish color, people were more likely to evacuate when they saw the houses than when they saw the squares, but randomizing the order of the arrays got rid of this effect. So in experiment 2, we increased the actual specificity of the information. So as a reminder, in experiment 1, we were always using these 10% increments. So the 100 icon arrays weren't actually more specific than the 10 icon arrays because the probabilities represented were the same. But in experiment 2, we actually made things more specific. So we subtracted 1 or 2% from our 10% increments to create this category of just below stimuli. Or we added 1 to 2% of risk to create this category of what we call just above stimuli. So it's just above or just below the 10% increments we used in the first study. Once again, we found that there was a significant difference between the icon arrays and the natural frequencies. People were more likely to evacuate when they saw the icon arrays. There was also this effect down here at the very low probability where people were more likely to evacuate for the natural frequencies. And I believe that was because people were misreading the stimuli. So if we said something like there's a 9 out of 100 chance that your house will be in the burn zone, people were misreading it as 90 and evacuating by mistake. But overall, we again saw higher evacuation rates for the icon arrays. So the most interesting finding from experiment 2 had to do with the comparison between the ordered and the randomized icon arrays. So these are the results from experiment 1, where we had these exact 10% increments. And again, you can see there were higher evacuation rates for the randomized arrays than for the ordered icon arrays. In experiment 2, when we added these just below stimuli, it didn't change the evacuation rates very much. If we subtract 1 to 2% of the risk, it doesn't really matter. People's evacuation rates stay mostly the same. But if we add 1 to 2% more risk in the just above stimuli, then the evacuation rates jumped quite a bit. And I'll just flip back and forth a couple times to show how big that jump is. And just as one example of how big this effect is, in the 40% risk condition, again, we're having an actual increase in risk of 1 to 2%, but the increase in evacuation rates was 34% on average here. So it's having a big effect on people's decisions. We looked at people's response times for these stimuli, and we did find that they were spending significantly longer on the randomized icon arrays than the ordered arrays, but still their average response times were about 2 seconds. So that's not long enough to actually count the icons in those arrays. So we believe that people are estimating how many icons are in the risky category, and they're consistently overestimating the risk in the randomized icon arrays, which is why we're getting such a big jump in evacuation rates. So in summary, these 2 experiments showed that numerical and visual representations of probability do lead to different decisions about risk, consistent with the prior studies in this area. The participants' decisions were more risk averse for the icon arrays. We found that when the icon arrays were ordered, the participants judged the same risk to be lower when the denominator is larger. And again, that's consistent with prior research. The participants judged the risk to be higher when the icons have higher iconicity. And we found that very small changes in risk can lead to very big changes in decisions. So we think there's some visual biases at play here, like when the icon array starts to fill in the next row, that leads to a big increase in the evacuation rates. In the randomized icon arrays, we found that the denominator and iconicity effects vanished. And we also found that participants seem to overestimate the risk in general. And that's because they don't seem to be taking the time to count the icons. They're just estimating the risk based on kind of the gist of how the icon array looks. And they seem to be consistently overestimating that risk. So in conclusion, this is another piece of evidence that the choice of representation really does matter to human cognition and human decision-making. Visualizations can make a risk seem more concrete or more deterministic to people, especially with specific aspects of the visualization design, like the iconicity and the ordering, can really have an influence on perception of risk. The visual icon arrays can also bias decision-making in some ways, like in our case where small changes in risk led to much higher evacuation rates. We also found that mental estimation also tends to lead to higher estimates of risk, because in our randomized icon arrays, we found that people weren't taking the time to count the icons. And so it seems they were using a process of mental estimation that also led to higher evacuation rates. So with that, I'm happy to take questions. Thank you.
Thank you, Laura. Thank you for your presentation. I think uncertainty is one of those topics that just brings up a lot of self-consideration when you're reading any paper on it. I don't feel like my education was very strong with dealing with uncertainty going through a public education. So I suspect education would have a lot to do with this, and of course visual literacy as well. But we got a few questions. The one that I see as most interesting that I'm going to pick, because we're a little short on time, there's a question that says, the icon filling in the next row seems like a perceptual gestalt effect. Can you speak to this?
Yes, so I think that is part of what's driving the jump in evacuation rates when it's going on to that next row. Yeah, so I agree that that's the most likely reason. But it's interesting that it's even a bigger effect when it's randomized than when we have that just one icon on the next row, because it's much harder to see that difference when it's randomized. But somehow that's leading to even larger evacuation rates, which again I think is because of the mental estimation process. If you look at the examples I have on the screen here, it does look like there's more in that right-hand column. But yeah, I think that's something that's worth a little more exploration.
Well, I agree that with your suggestion that there's a lot of extra investigation that could take place here with so many aspects of what this work suggests, especially on the cognitive modeling of what's going on inside our heads. So thank you for the contribution and the thoughtfulness that it derives in the reader. I'm going to move on to the next presenter, where we've used up our 3 minutes of slippage time, but I think the stream will last maybe 5 minutes, so we'll keep trying to give everybody their time. The next presenter is Arran Zeyu, and he has 2 co-authors that let him present, as well as his title for his presentation. Take it away, Arran.
Yeah, cool. Thank you so much for the introduction. Yeah. Hi, folks. I'm Arran from UNC Chapel Hill. The title of our work is Using Counterfactuals to Improve Causal Inference from Realizations. I'll be sharing this work on behalf of my colleague David Borland from the Renzi Institute and David Gotz from UNC Chapel Hill. So this work is a position article from the CG&A visualization viewpoints. Starting from a very simple visualization, that is, this chart shows the data of success rate of 2 kidney stone treatments A and B. So let's think about it. What can we learn from this chart? Very simply, we can say treatment B causes a higher success rate than treatment A. And this is when people looking at the chart, it hints us we should use treatment B because it caused a better outcome in terms of the success rate. So this is how we got a causal conclusion from a simple visualizations. But it may not necessarily to be true since visualization only show correlation. For example, patients using treatment A may be in more severe conditions versus those in treatment B, and that causes those differences. Anyway, like what we're showing, like many existing other studies have also validated that visualization consumers draw causal conclusions from those very common statistical charts. And technically, for better understanding those causal relations from the visualized data, there have been many other approaches. One option to make it better is to adopt graphical causal models to capture the causal graph information from data, as for the most previous work on visual causal inference techniques, but it may not always be the best way. For example, due to the complexity of data and models, effectively computing and modeling causal relations remains challenging, even with the support of very up-to-date normal machine learning models. From this work, we identify 4 key challenges for the visual causal inference technologies. First of all, we identified graphical causal models are sensitive to noisy, incomplete, missing, invalid, confounded, or even unrecorded data. And today, most of our datasets are not originally created for causal inference tasks. Therefore, it can exhibit those kind of data quality issues, especially for those real-world ones. And for the second concerns, we identify a single dataset can contain hundreds of thousands of unique variables, for example, especially in those data-driven healthcare cases. And most applications using colorgraph modeling specifically focus on relatively small graphs with a very limited number of variables and interactions, for example, 10 to 20. And third, the current causal models must also capture a direction of those causal relationships. That is, they should have a from nodes which have a causal effect upon the 2 nodes for each of the link, which makes the computation a lot more complex. Lastly, existing visual analytic systems primarily focus on the prediction and intervention levels in causal relations, neglecting the counterfactual reasoning. In this work, in this presentation paper, we propose to use counterfactuals as an alternative of existing approach to support visual causal inference, especially with those common statistical charts. So what is counterfactual? Counterfactuals are hypothetical scenarios that enable us to examine potential outcomes across different scenarios in which only one particular factor is altered. Isolating the factor enables improved reasoning about an understanding of causal relationships involving in this factor. For example, what if the Earth were square? And what does it mean, especially in terms of visualization context? We connected it with one of the most basic techniques for exploratory analysis, filtering, where people often use filters to create point of interest subsets to better explore their interested data. Still, let's go back to the very early kidney stone treatment example. Assuming we have a data set of patients with two different kidney stone treatments of side and the stones. So we want to compare the effectiveness between these two treatments, A and B. To achieve this goal, the first step is usually we will filter the data using these two treatments. We therefore got an included data subset which include all the patients with treatment A. And it also created an excluded data subset which contains all patients with treatment B. But what about counterfactuals? Here, in our definition, we define the counterfactual data subset is computed based from the excluded datasets that are similar to those from the included subset in other dimensions. While in this way, we can have a counterfactual subset including patients using treatment B, while in all the other dimensions, they are similar to the patients with treatment A. And the rest, we call them remainders, which contains patients with treatment B, and meanwhile, they are not similar. In this case, it's about stone size to those with treatment A. So now we have all those different data subsets. If we go back to the very early bar chart visualization as shown here, what will their counterfactual words look like? Very similarly, we are adding one more data column here. That is our the right side. The right side of the chart shows the counterfactuals version of these kidney stone examples, and the middle part shows a counterfactual subset visualization of treatment B. What we can observe here is the counterfactual version of treatment B has a lower success rate than treatment A, and this actually indicates treatment A is more effective than treatment B when considering patients in the same conditions. And this is one of the most famous example of Simpson's paradox, and currently you successfully beat it. We also show the overall data sets here. Now the counterfactual visualizations lead us to think about things differently, while it keeps the simplicity, then going to complex graphical causal models with just simple statistical charts. But the kidney stone example is so simple, so probably you can resolve it within one bite. Maybe you want to ask, what about more complex cases? So we have a bit more demonstrations. We propose a system in the past called CoFact. It leverages counterfactuals to help better communication the relationships between variables of interest. In this work, we show counterfactual visualizations, even using common line graphs or bar charts, can help users better interpret relations of data variables. However, CoFact is just the start of the counterfactual-based analytics. There could be more potentials to make them even better. We point out 4 open opportunities of using counterfactuals to better support viral causal inference, where the first one is measures of evaluating the quality of a counterfactual subset, which is to define what makes a good counterfactual subset. We know that this is a especially difficult problem because of the similarity is inherently both a task or data-dependent question. Even for the same data set, the most similar could be somehow different depending upon which analytical question is being asked. Secondly, we identify improving the viral communications of counterfactuals is very important to find a best way to communicate such information within visualizations, because counterfactuals is not a common knowledge for the vast audience usually. And this will make these methods more accessible to a larger set of audience. And last, we identify we need to have some better cognitive models in terms of how people perceive causality from charts. And we try to we also need to find a way to model those causality perception to get a better understanding of how data realizations can convey causality to users. And last, this work is made possible by all of our fabulous authors and is supported by the following NSF grants. Also, please feel free to check our other related work on the viral causal inference topics, including using counterfactuals as guidance in viral analytics, as well as measuring the perception of causality with common realizations in at base also. Yeah. Thank you so much, and I'll be happy to take any questions.
Thank you very much, Arran. That's really great work. As I read your paper, I've immediately thought that it's a very powerful educational resource, because I don't think counterfactuals are something that have been presented so effectively, at least in my limited travels. It's not something that's in my direct experience, but you make a strong argument. I don't see anybody asking any questions, so I suspect it's hard to come up with a counter example as to why your paper shouldn't be very powerful in the way that it's written. So I thank you again for your participation in this session, and I'm going to move on to the last author only because we're running out of time. Thank you again.
Yeah, thank you so much.
Our last presenter is Timothy Major, and he will be presenting on behalf of Rahul Basol, and I'll let him just take it away. Take it away, Timothy.
All right, thank you so much. Yeah, my name's Tim Major. I'm with Accenture Data and AI, and I'm presenting on behalf of Rahul Basol, and we're going to talk about generative AI today. So it's been, you'll find the camera here. So it's been nearly about 2 years since ChatGPT was introduced, and that set off a firestorm of interest in generative AI, right? With some pundits referring to the event as the iPhone moment for AI. And an important frontier for this technology is the world of data. In practice, we're hearing left and right about how AI and generative AI and Viz are coming closer and closer together. While in research, we're building upon rich prior knowledge in topics such as visual analytics and natural language interfaces to look at how generative AI models can help visualize and be visualized. But now there's a much more intense spotlight with these things being seen as inevitable and mainstream. The generative AI is more than the popular conception of a chat box on a website. When working with data and data visualizations, it has the potential to do more than just answer questions. And I want to today present an end-to-end framework laying out the different phases of the visualization workflow, from creation to consumption to scaling and governance, and examine the challenges and opportunities along the way. And then we're going to look forward with a strong call to action to the visualization community, both researchers and practitioners. Now, I recognize that the examples we present here are not exhaustive. Things are very fluid, moving very quickly, but we wanted to rather give a starting point to anchor the visualization field in the shift that is occurring. I want to briefly pause here and reemphasize that we are working with the broader definition of generative AI, not just the popular LLM one. A generative AI system is any AI system that uses existing media to create new plausible media. So here we present the end-to-end visualization workflow based on a holistic perspective of real-world visualization practice. It's important to consider how generative AI supports cross-disciplinary teams of designers, creators, developers, and data engineers. Each phase of the workflow encompasses a related set of activities, such as gathering user and design requirements in phase A. And it should be noted that the process is rarely linear, but something rather iterative. The inner boxes represent tasks that can be impacted by generative AI. And we posit that generative AI capabilities for visualization can be grouped into 3 highly complementary types: creativity, assistance, and automation. In the interest of time, I will call out through a few examples these types of generative AI as I discuss 4 major sections or groupings of phases. Please refer to our paper for more details and more examples. I'll also note that in some of these illustrations, we use a chat bubble to represent a prompt for generative AI. However, natural language is not the only input modality. The first section comprises the phases related to creating visualization artifacts. Here, teams are focused on gathering requirements, organizing, wrangling, and exploring data, then designing, building, and deploying solutions. Here are a few examples of how generative AI can be used across its 3 types. It can be used as an assistant to produce user and design requirements based on specific questions and needs. Generative AI can also automate the process of cleaning and/or producing synthetic data in many different formats. Or it can provide design alternatives for a selection of charts helping designers explore creative possibilities. Challenges in this phase here include the tuning of generative AI models to provide responses to a tailored specific domain. It requires heavy uplift and impacts the quality of requirements and designs produced. In addition, for many of the activities, generative AI must interact with other systems to produce output. Ensuring that those systems are properly integrated and contextual information is not lost is difficult. Perhaps most focus on generative AI opportunities in visualization have been occurring in the consumption phase, where the promise is faster, more direct answers with data. However, there are many more opportunities to enhance information and insights for end users using generative AI. It can produce key insights, chart annotations, explanations of what is shown, and summaries of data patterns, as well as dynamic guidance. Again, often in conjunction with other systems that have already been developed. The challenges here deal with underspecified and ambiguous prompts, introducing difficulties when natural language is used as the input modality. Discoverability is a related issue to this. In addition, if the generative AI model sits between an analytical system and the end user interpreting and modifying responses, validating those results is critical. After visualization artifacts have been deployed, understanding if they are effective and provide value is critical for research and organizations. Here, generative AI can support critique by generating rubrics for evaluators and producing reports on feedback and issues with current artifacts. Or it can be used to consolidate and simplify existing assets and reduce the proliferation of one-off redundant artifacts. However, while general issues of usability and usefulness can be surfaced using off-the-shelf generative AI models, evaluation approaches are still challenging and depend, again, on the breadth and depth of the data that can be provided to train these models. The methodical creation of robust data sets to tune models is critical here. Finally, to ensure that organizations can benefit from data, analytics, and AI, a strong data culture and collaborative mindset must be established. Generative AI can support data literacy by automatically creating documentation, training materials, and FAQs. Its ability to support collaborative workflows is also very important, as the flow of generated insights, notes, and summaries up and down and across an organization can be a very vital information stream for decision-making. However, technology alone does not create a data-driven culture and foster collaboration. Generative AI is just a piece of the puzzle here and must be used responsibly. Users need to be trained to use generative AI systems with care and caution within the appropriate legal and data protection frameworks. So, in our work, we present an end-to-end perspective on the opportunities and challenges for generative AI within Viz. And we also classify the types of generative AI capabilities as creativity, assistance, and automation. And as these generative AI capabilities shift and emerge, this framework can serve as a useful anchor to the community. Again, the examples shared here are not exhaustive. We would like to explore more opportunities, particularly during the later phases of the visualization workflow. However, what is clear is there's no turning back from the tighter integration of AI and Viz. We share a call to action along two axes, research and technology and community. For research and technology, generative AI models for Viz require more data and a clear evaluation approach. Recommendations are needed on how to best use LLMs and other generative AI models as orchestrators to other systems. And we're really seeing human and AI interaction coming to the forefront. We're no longer concerned with like a single best visualization in isolation, but rather need to develop guidance on how to support rapid iterative querying in pursuit of situated decision-making. And this sort of shift to direct modalities require guardrails to be developed. For example, how do we ensure answers are correct? How do we handle invalid and unanswerable queries? How do we present information in a way that users can use the results in confidence or steer the AI if correction is needed? This is related to visualization for generative AI instead of generative AI for visualization, which we would love to see more research and believe there's opportunities in. And finally, for better or for worse, the creation of visualizations is becoming increasingly commoditized in practice. And while it's no longer good enough to just be a visualization creator, the value of visualization is not diminished. In fact, it's more important than ever. Visualization is the medium for communication between human data and AI. And what we need to be doing as a community is teaching and nurturing talent and injecting visualization design and knowledge into AI systems. So that's a very brief overview of some of the things we covered in our paper. Here's a link. Thank you for listening to our talk, and happy to take any questions.
Thank you, Tim, for that presentation. That's wonderful. I have to admit that I have used this paper in my understanding and exploring artificial intelligence course at RISD, and have kind of asked each student to apply your roadmap to their own personal workflows and talk about creativity in that. And it was really great because then I could also put in a plug for using their talents with data visualization at the same time. So I appreciate that. I'm not seeing any questions, but your paper certainly brings up a lot of questions for each of us as we think about how AI might possibly improve, challenge, conflict with our workflows, and deal with it, grasp with it, and get ready for the AI that seems to be getting great investment. So it's certainly going to be producing many tools. That's how I think about it, and I appreciate your paper because it really encapsulates much about it. Anybody else have a question? I'm going to open it up to our presenters to question anything about the session. Was there anything that came to mind that you wanted to say before we sign off? No? Okay, well, I just want to applaud you all one more time. Appreciate you being here. Appreciate you participating with CG&A and considering the magazine as a place to publish. We can continue our discussion on Discord via the Bayshore 3 room that's listed within the Discord tool. Note that the email addresses for each of the presenters is on the session page. So you click on their name, you have a way to contact them via email. I will say that Computer Graphics and Applications is an online magazine I find useful for spontaneous and serendipitous thought on the subject of computer graphics and applications. Most issues cover a special issue of a special topic that attempts to represent the taxonomy of the issues, solutions, and research being done associated with that issue or that special topic. Any presenter or attendee who has a special idea or a special issue can contact Chris Weaver. He's available via email, cweaver@ou.edu, CWEAVER@ou.edu. And with that, I will conclude our session and look forward to the next time I have some opportunity to be with y'all. Thanks again.